Welcome to topic 9.6. This is our introduction to gas laws. So we're kind of getting away from looking at phase changes and interpreting temperature and pressure, but start looking at gases and their behavior. So we have three laws we're going to look at today. The thing with today's topic is I never expect you to memorize the equations, but rather how to use them. And quite frankly, I don't need you to know whose law is whose. So Boyle is the first individual we're going to look at, and he found the relationship between volume and pressure. So he found that this is an indirect relationship. So what we see with an indirect relationship is not necessarily that it's a negative slope, but rather an exponential slope, and in this case, exponential decay. So it could be exponential growth also. What we're seeing is that as pressure, and again, going back to what is and what causes pressure with gases, it's all about collisions. So think of this as the number of collisions is increasing. Well, how do we make collisions increase? Volume has to go down. So the smaller the space a gas has to occupy, the more collisions and frequency of collisions is going to go up. So again, this is kind of just reiterating what I'm saying. The one thing that we hold true with Boyle's law is that temperature is a constant factor. It's very rare that temperature can remain constant while pressure and volume are the only things being influenced. In most real world application and things that we see, temperature also changes. In labs, we have better control over that. So again, we're not saying temperature can change. It's looking at just the relationship of pressure and volume. That develops this equation P1 V1 equals P2 V2, where P stands for pressure and V stands for volume. Those subscript ones just imply like these are the bonded, connected, kind of starting pressure, starting volume. The twos are like this is my ending pressure, ending volume. And we'll show the application in this one example. Here we have a volume, our sample of gas has a volume of 150 milliliters. So I'm going to go ahead and highlight that. And again, that is telling me that milliliters is a unit of volume. So this is what we're starting with, V1. And the corresponding condition that is experiencing here is a pressure of 0.947 atmospheres or ATM. So that is P2, or excuse me, P1. So then it says, what will the volume of the gas be? So we're solving for volume. So what volume tells me that V2 is what I am solving for. And that's my big old question mark. And that means here that I have an atmosphere pressure. And so this is telling me the P2 condition. Okay. So from there, that leads me into Boyle's law of working with P1 V1 is equal to P2 V2. I can go ahead and substitute things in. So I have 0.947 ATM at 150 milliliters. I can see that pressure is increasing, meaning more collisions. So that means I can make a prediction that my volume should be going down. Solving for an x then is what's going on here. So I'm going to divide by 0.987 to allow x to be by itself. From here, I take 0.947 times my 150, and then I divide that out by 0.987. I can keep 3 sig figs, so with rounding, it looks like 144 milliliters is going to be my answer here. Okay. The next law we're going to look at is Charles' law. Charles will notice that it, again, negative positive slope has nothing to do with this. We see a nice linear slope here, not exponential. And so this is a direct relationship, meaning if you go up by 1, it goes up by 1, in this case being temperature and volume. So again, temperature is a measure of kinetic energy, volume, the amount of space. So we find that a gas, because it's so unique in that there's so minimal particle attraction, that most of a gas is empty space. And as we add heat, meaning adding kinetic energy, those particles just start to expand further and further out because those attractive forces are next to none in a gas. And so we find that, again, they are directly linked. So again, we can see the unique property of expansion and contraction of a gas. Part of our activity next week will look at that as well. The other thing that Charles did, going back to his graph, is he looked at this relationship here with volume and temperature. And he asked himself, where would this graph cross if I were to extrapolate data and go backwards in terms of volume? And he wanted to know what would happen if volume was zero. What temperature would it cross at? And he found that when he used real data and graphed it backwards, he found that the volume of a gas crosses with a very unique temperature. And it crosses at minus 273 degrees Celsius, which is absolute zero. Absolute zero is where all particle motion stops, and that helps lead into this next tidbit. Is his relationship is volume and temperature. And so when we discuss gas laws, we always use the temperature scale of Kelvin, where Kelvin is the degrees Celsius plus 273, because Kelvin starts at zero, which is equal to that minus 273 degrees Celsius mark. And so that is, again, hypothetically, where a gas would reach a volume of zero. Why we need Kelvin for our gas laws is that when we have negative temperatures, the math doesn't work out correctly. So Kelvin takes care of that issue of not having to worry about negative temperatures, because there is no such thing as a negative temperature in Kelvin. So here it asks, a container of oxygen has a volume of 349 milliliters. So we can see that milliliters is a volume unit. And it's at a temperature then of 22 degrees Celsius. So again, Celsius being a temperature unit. But I also know that then I need to convert that to Kelvin. And all that is adding 273. So that is 295 Kelvin, not degrees Kelvin, just K. It asks what volume. So we're trying to solve for V2. We're looking at how does this change. And we have the new corresponding temperature, that the temperature is increasing to 50 degrees Celsius. So this is T2, which also needs to be converted over. So add 273 to it to get 323 Kelvin. That then leads me to my equation that V1 over T1 is equal to V2 over T2. Plugging in 349 milliliters over 295 Kelvin is equal to X over 323 Kelvin. Temperature went up, volume should hopefully go up when we look at the results of this. To solve, I'm going to go ahead and cross multiply. So I would get, and let me backtrack here, 349 milliliters times 323 Kelvin is equal to 295 Kelvin times X. The order, the side that it's on, doesn't matter. But we end up doing the same math of dividing by 295. Okay, so we take 349 times 323, divide that out by 295, and we can keep 3 sig figs. X, representing volume 2, is going to be 382. Kelvin is canceling, and this is in milliliters. Okay. The next law that we're going to look at for today is the relationship between pressure and temperature. So like Charles' law, we find that pressure goes up directly with temperature. If one goes up, the other goes up. If one goes down, the other goes down. Again, pressure is collisions, and collisions is relating to temperature, in this case meaning energy, which the more energy you have, the more collisions you're going to have. That should kind of make sense. So looking at the last problem and the equation here is it's very, very similar to Charles. So instead of volume now, we have pressure. P1 over T1 equals P2 over T2. Like Charles, we have to use the Kelvin temperature scale. So again, taking a look, we have 4.4 atmospheres, and I see 6.5 atmospheres. Knowing the unit of atmospheres, I know that this is my starting pressure, and this is my ending pressure. So the other thing I have to work with is 25 Celsius, which I know Celsius is a unit of temperature. And by adding 273, I get 298 Kelvin. Okay. So in this problem, it's asking for what temperature. And in this specific problem, it is specifying a unit here. We'll talk about more of what to do with that here in a second. So the whole premise that this problem will build on is that P1 over T1 is equal to P2 over T2, where 4.4 atmospheres over 298 Kelvin is equal to my new pressure, 6.5, which I see the pressure is going up. So that means my answer should also go up. Okay. Like the last problem, we're going to go ahead and cross multiply here. So I get 298 Kelvin times 6.5 ATM is equal to 4.4 times X. Divide by 4.4. Okay. So we get 298 times 6.5. Divide that by 4.4. I can keep not 4, but 3 sig figs. So 440 with the decimal will give me 3 sig figs. And ATM is canceling. And I can see that, yep, temperature went up, and that's in Kelvin. The problem specifically asked to solve for our answer in Celsius. So that part, you still want to put it into Kelvin and then take it back out of Kelvin, because again of those negative temperatures. So 273 gets subtracted, and that gives us an answer of 167 degrees Celsius. Okay, so I'm not going to work out everything with the last 3 problems, but I'm going to talk a little bit about them. When I look at this problem, I can see that I have liters here. Okay, so liters is a unit of volume. Okay, and then I can see that I have a temperature of Celsius. So I have degrees Celsius is a temperature 1. So what I'm getting at is your units will decide what formula you should use. So since I have volume and since I have temperature, the formula that would be used here is that V1 over T1 is equal to V2 over T2, is how I would decide that that's the equation I need to use. In this one, I have a liter. The unit liter is a unit of volume. Okay? Atmospheres is a unit of pressure. So this one is working with volume and pressure. So that means the equation is the V1 P1 equals V2 P2. The last equation says that we have 1.8 atmospheres. So I know that atmospheres is a unit of pressure and that degrees Celsius is a unit of temperature. So the formula that would be necessary here would be P1 over T1 equals P2 over T2. So make sure you're carefully identifying your units, because that will decide which formula you should use, and make sure your Celsius gets changed to Kelvin.